Solving linear systems by using a table. There's a table feature on your calculator, and we looked at this in the last unit to verify that two expressions were equivalent. We can also use this feature to solve certain systems of equations. This feature also has some limitations, even more so than the graphing method. So first off, each equation must be first solved for y, because we're going to first enter those equations on the same screen that we did for graphing. But then the table feature can only find the intersection point if the x-coordinate of the solution is an integer, since we currently have our table set up to show outputs only for the integer values of x. Now the calculator will find, again, just an approximate solution, so we do need to verify that what we think is the solution really is by checking to make sure that it does actually satisfy all the equations in the system. So example 6 asks us to solve the following system using the table feature of the calculator. Okay, so again, one of our important verbs here. So to solve a system, in this case our system has variables x and y, so we're being asked again to find all ordered pairs that make both equations true. Okay. Or in thinking about the graph, we're trying to find the ordered pairs that both graphs share or have in common. So our first equation is 3x plus 2y equals 15, and our other equation is y equals 1/2 plus 2x. So the first thing that we need to do is we need to solve for y in each equation. And again, solve for y, we need to know what that means. Again, we need to get it in the form y equals, and then we need an expression on the other side with no y in it. So if we take our first equation, 3x plus 2y equals 15, we're trying to solve for y. So again, this is a positive 3x, so the first thing we're going to do is we're going to subtract 3x from both sides, and that leaves us with 2y equals 15 minus 3x. And then to get y by itself, we're going to divide both sides by 2. So again, when we use this long bar, we need that whole expression divided by 2. So we're going to get y equals, and again, just like we distribute multiplication over addition and subtraction, we also distribute division over addition and subtraction. So this 15 needs to be divided by 2. And this 3 needs to be divided by 2. So we're going to get 15 halves subtract 3 halves x. And our second equation is already solved for y. We have a y equals, and over here there's no y in this expression. So this one's already solved for y. Alright, so now we can push y equal, and again kind of scroll up and down that screen and clear out any existing equations you have. And then we're going to enter the two equations from above, keeping in mind that we're going to put parentheses around each of our fractions. So next to y1, we're going to type a parentheses, 15 divided by 2, and then close that parentheses. Subtract, again another parentheses, 3 divided by 2, and another parentheses to close that. And then again, to type an x, you have a key on your calculator that looks like this. Okay, so you're going to push that button to type an x. Then we're going to arrow down, and next to y2, again, parentheses around our fraction. So parentheses 1 divided by 2, and then close those parentheses, and then plus 2x. And again, to type our x, we're going to push the button that looks like this. All right, so now we have our two equations in there. So to see the table feature, we're going to push second graph to see the table of input and output values. And in the last unit, we set this so that these were integers. We can set them to different values, but we had set these to increment by 1 starting at 0. Okay, now some of you, your screen may be in a different place here depending on where you last looked at it. So you may need to either scroll up or scroll down until you see your table starting at 0. 0, 1, 2, 3, 4, 5, 6. And then your screen should look like what is here. Okay, if your numbers don't match what's here, go back and push y equals and make sure that you've typed these equations correctly, especially the x's. Okay, if we forget the x's, we just get constant values in each of these columns. Okay, so now we're trying to, if we're thinking about the graph, we're trying to find a point that they both have in common. So if we take this first row, for example, we have an input of 0, gives us an output of 7.5. Okay, so this point is on the graph of equation 1. But for an input of 0, the output is 0.5 for equation 2. So at 0, the point is 0.5 on the graph of equation 2. Okay, so they don't share a point in common here when the input is 0. Okay, but if we look down through here, we do see at 2, the point 2, comma 4.5 is on the graph of equation 1, and for an input of 2, the output y2 was 4.5 also. So the point 2, 4.5, is also on the graph of equation 2. Okay, so these two graphs intersect at this point. So the solution to the system is 2, 4.5. And so now to verify it really is a solution, we need to make sure that that point really does make both equations in our system true. So again, starting with the first equation and remembering to put parentheses around each variable before we substitute. So we get 3 times 2 plus 2 times 4.5. And we're checking to see if that equals 15. So we're going to get 6 plus 9 equals 15. 15 equals 15, which is true. Okay, so that tells us that 2, 4.5 is a solution to this equation, to 3x plus 2y equals 15. Okay, but to be a solution to the system, it also has to be a solution to the other equation. So again, taking our second equation, and putting parentheses around each variable before we substitute values. So in for y, we're going to substitute 4.5, and for x, we're going to substitute 2. So we get 4.5 equals 1/2 plus 4. So 4.5 equals 4.5, which is true. So we know that this point, 2, 4.5, is a solution to the second equation, y equals 1/2 plus 2x. So since it's a solution to both equations, we know that 2, 4.5 is also a solution to the system. Okay, this set of equations, 3x plus 2y equals 15, and 1/2 plus 2x, y equals 1/2 plus 2x. Okay, so again, we're trying to find a point that they both had in common in the table. It must be where the graphs intersect, and when we verified, that point actually was a solution to both equations. So that point also has to be a solution then to our system.